Hey everyone, it is Wednesday. We're going to go over some information regarding the final, finishing up nuclear chem, and just a general overview of what the next couple of weeks are going to look like. So to start off, um, I'll be having your essays finished by Friday. And so Friday, I'm going to send out an email to everyone, parents and students, and just give you a little extra detail about the next couple of weeks as far as finals week, things like that. And so by Friday, you should have a grade up to date. Um, and I know we have one assignment that's still on Google Classroom, but we'll have a grade that's up to date, and you'll see, and I'll have a little bit of a numbers game to let you know how the final should potentially influence your grade. You have until June 9th to, if you elected for a grade in the class, you've already emailed me, you have till June 9th to potentially take that away and just go back to credit, no credit if you desire, if you want to. Otherwise, whoever emailed me on that saying they wanted a grade, I am sticking to that unless you notify me. And all this is going to be in the email, but it's just a little heads up to what's coming up on Friday. Basically, we have another week and then we have finals. And so finals week, I'm going to open up a quiz, which is going to be 20 questions, and you'll have all week to finish it. So whatever time works best for you. I would allot somewhere between 30, 40 minutes to take it, even though it shouldn't take as long. But about 30, 40 minutes as a maximum should be what I expect it should take. But 20 questions, Google quiz, you get on there like we've done before and just answer the questions. And then when everyone has finished the quiz, then I'll be able to release it and just release the scores. I'll probably have it set to be due by that Thursday. They'll give me a day to finish everything and get this all everything squared away and your grades finalized. So let's talk about the about nuclear chem first, and then I'll finish with a little bit of the finals review PDF that is put on Google Classroom. So let's go to this. So the last little bit I want to talk about is how to look at a chemical reaction from a nuclear chem point of view. We talked about alpha decay, beta decay, and I posted some videos to help you recognize it as well. I'll go through some of that again. And then what we're going to do is represent a nuclear decay process using a chemical reaction. And it's a little bit of balance in equations. But I think once you see it a couple times, you'll get the hang of it. And I'm going to put up a little practice assignment to go online to help you look at that. And we can look at a couple of those examples and do a few together. So let's review a few things in the beginning. We have several different types of decay. We've got alpha decay, beta decay, there's positron emission, there's electron capture. On the final, I'm only going to ask you to know about alpha and beta decay, but for purposes of doing our work, identifying what a positron is and what electron capture looks like will also help us. There's also gamma decay, but it's not going to be in the balanced equation way that others will be in there. So I'll get to that in just a moment. So let's start with alpha and beta. So atoms go through radioactive decay when their nucleus is unstable, meaning there's a disproportionate amount of protons and neutrons to where it's outside of this comfortable ratio. So let's say we have a magnesium atom. Magnesium has 12 protons, and typically it has 12 neutrons. But let's say this particular sample has 16 neutrons. So this is the atomic symbol. And you're going to have to know what each of these means. The bottom left number is the atomic number. This is the number of protons. And the top left number is the mass number or the isotope number. So this is protons plus neutrons. So if I were to ask how many neutrons are in this particular sample, you take 28 minus 12. So this sample has 12 protons, and then 28 minus 12 gets us 16, and those are neutrons. The N is our symbol for neutron with a little 0 because of its charge, and the P is going to be our proton symbol for proton, and then you got the positive charge on that as well. So that's analyzing the atomic symbol, and we're going to take this isotope and have it undergo alpha decay. So alpha decay would be this atom being unstable and breaking down. And when this atom breaks down, it's going to release the equivalent of a helium nucleus. This is an alpha particle. Now this technically has a charge on it because it's just 2 protons and 2 neutrons. 2 protons, 2 neutrons. So this is positively charged. But in nuclear equations, we don't necessarily focus on the charge too much. So you might see a +2 up there as far as 2 protons without the 2 electrons to balance out the charge. But if you don't see it, don't freak out. The alpha particle is a positively charged particle. So I'm going to leave the +2 there. Now there's another way you might see it. You might see the script A, and that just means alpha particle, but these are essentially the same thing. So just to keep our connection to what an alpha particle is, I'm going to write it as HE, but you might also see that script A symbol as well. Now, what happens is we're going to have a way to predict what the product's going to be. And it's just making sure that everything's balanced on the left side and the right side with respect to their mass value and their protons. So we're thinking it's some element with a number on the bottom left and a number on the top left. So what could these numbers be? Let's look at the bottom left number first. If everything needs to be balanced on both sides, that means the total number of protons need to be the same on both sides. So 2 and something should get us 12. And it just so happens that this is 10. The idea is this atom, this magnesium atom, is kicking off 2 protons and 2 neutrons. And so what's left over? So it's not magnesium anymore, it's whatever has 10 protons, which in this case is going to be neon. So once we know how many protons are there, we can say that this is neon. If it's 10 protons, it's going to be neon. And then with the top left number, we also have to do the same process with the other top left numbers. So 4 and something gets me 28. And so the remainder is going to be 24. So if a mass of 4 is kicked off, which is the combination of 2 protons and 2 neutrons, if the atom loses a mass of 4, then the remainder is going to be 24, which is neon with 24 as its mass number, which means I can subtract off the 10 and say that there's 14 neutrons. Now neon, this is not a stable version of neon. Neon would undergo some more radioactive decay after that, but this is just an example of an atom going through alpha decay. So part of your job would be to just predict what is left over if I gave you the core of the balanced equation. If I tell you it's magnesium and I tell you it's going through alpha decay and I give you the numbers, could you predict what the unknown is? And we'll see that in a couple example problems. So that's the pattern for alpha decay. To give you another example, let's say I have calcium, and calcium is the 20th element, and let's say it's calcium 42. Calcium 42 is undergoing alpha decay, which means it's kicking off a helium nucleus. What is the other product? Well, the bottom numbers need to add up to equal to 20, and the top numbers need to add up to equal 42, so that everything is balanced on both sides of the equation. So 2 and 18 will get me 20, and 4 and 38 will get me 42. So just making sure that they add up correctly. And then we can ask, what element is that? What element is number 18? So we'll go to our periodic table and see that element 18 is argon. And that's it. The result of calcium 42, and this is another way to label that isotope, is to write out the name and just tell us the mass number. That's the isotope number. Calcium-42 undergoing alpha decay will release that alpha particle and also result in an argon-38 isotope remaining. The atom actually changes its element. So now let's look at beta. Beta decay is an interesting thing that happens, and I'm going to give you an example that something happens in your body. One of the very rare isotopes of carbon is 14. It's naturally occurring, but it's significantly less than 1%. Excuse me. Significantly less than 1%. So when carbon-14, the carbon-14 isotope undergoes beta decay, it's going to kick off a beta particle. And a beta particle is essentially an electron. And the way that we represent electrons in a chemical equation is with a lower left number of 0, because it doesn't represent any protons. It has, this particle consists of 0 protons. And it actually has a -1 effect on the mass. So, oh, excuse me, got that backwards. 0 mass, excuse me, and a -1 effect on the protons. It doesn't have any protons. It's a way for the carbon atom to go from 6 protons to a total of 7 protons. Essentially, what's happening is a neutron is changing into a proton, which neutrons have a mass of 1, protons have a mass of 1, so there's no mass change. There's no net mass change during a beta decay, but it's a way of the atom to increase its proton count by 1. So -1 and something needs to get me to 6. And so this would have to be 7. And I wrote an N there preemptively, just knowing that there'd be 7 protons. This is a way of carbon changing into nitrogen, but keeping the same mass value. Now, nitrogen-14 is one of the most common isotopes of nitrogen, so the result of this would actually be a stable element. This one's a little trickier just to notice, just to track with the negative numbers, but essentially beta decay does not change the mass, but it raises the proton count of the atom that's undergoing beta decay. And this is an electron-like particle that's kicked off. It leaves the nucleus, it leaves the atom. It has a negative charge, so you might see a charge in there as far as -1. But again, with nuclear reactions, we don't focus as much on the charges as we do on the proton count and the mass value. These are the 2 main ones that you need to know. These are the ones that could show up on the final. The other ones that will be helpful for, that I'll go over, will be helpful for doing the practice assignment, where I have several of these equations. You're just going to practice filling in the blank, guessing the unknown. So I'll just do positron emission and electron capture really quick. So positron emission is something that is a process that releases a positron. And a positron has the symbol just like an electron, but it is a positively charged electron. So instead of a -1 in the lower left, it's going to be a +1 in the lower left based on how it affects the atom. It's a way of a neutron changing back into a proton. Excuse me, a proton changing back into a neutron. So this actually brings the proton count down by 1 when you look and see how it affects the balanced equation, but it does not change the mass. These are the 2 things that positron emission does. So let's go back and look at the opposite. Let's take nitrogen, say nitrogen-12. Let's say this is a pretty low mass isotope of nitrogen. It's unstable, and so it needs a way to adjust its proton neutron count. And this could go through positron emission. So we know it's positron emission, so we can write the positron, again, not really focusing too much on the charge, just the atomic number and the mass number. And what particle could go in this blank to complete the addition? 1 and something. So a 6 and a +1 will give me 7. So we know that this has to be a 6 in the lower left. And on the top left, the mass should not change. And so this is an example of nitrogen changing into carbon, specifically nitrogen isotope 12, changing to carbon isotope 12 as a result of positron emission. And the fourth example that you might have to deal with is electron capture. This is pretty rare. This is essentially where an electron-like particle is absorbed, brought into the nucleus. So you've got your atom. An electron, which has this symbol, is going to enter the atom and fuse with the particle in the nucleus. So let's take an oxygen atom. Oxygen is the 8th element. And oxygen is undergoing positron or electron capture, which in this case is the only time you're really going to see an electron as a reactant. So this will be, let's say this is a heavy isotope of oxygen. This is oxygen 14. An electron comes into the nucleus and it essentially changes a proton into a neutron. So this is a way of 8 minus 1 will get me 7 to make sure both sides are balanced. And this is a way of light isotope of oxygen changing into a stable isotope of nitrogen. So this is what a electron capture equation looks like. The big parts about this is the electron enters the atom instead of leaving. And this is where a proton will change back to a neutron. And then again, no mass change on this one. So several of these have 0 mass change. So there's minor tweaks to the proton-neutron ratio. The one that has the large mass change is alpha decay, and that's why it's one of the most common. A couple other things that you're going to see is fission and fusion. Fusion has been in science fiction movies for a while, basically this illustrious power source that could cure everything. We have fusion reactors, but they're very expensive to maintain. You have to have these reactors up to 3,000 degrees Celsius, if not even hotter. I'm trying to remember that number off the top of my head. But essentially, a simple fusion reaction that happens all the time in the sun is hydrogen fusion. So we want to think, how would we write the symbol for a hydrogen atom with 0 neutrons? Well, hydrogen always has to have a 1 in the lower left, but if hydrogen has 0 neutrons, it's going to have a 1 on the top. So this is the isotope hydrogen 1. This is the most common isotope of hydrogen. And let's say over here we have a heavier isotope of hydrogen, hydrogen 2. And the name for hydrogen 2 is a deuteron. And the name for a hydrogen 3 isotope is called tritium. Another name that kind of shows up in science fiction every once in a while, the word tritium. So in this particular reaction, we're going to fuse hydrogen 1 with hydrogen 2, 2 different isotopes of hydrogen. And we're going to see, so we'll see 2 elements on the left side, and we're going to synthesize them together, kind of like a synthesis reaction we would see. And we're going to have something, but it's not going to be hydrogen, it's going to be helium, because if we add the protons together and fuse them together, we get a different element. If we add the masses together, we're going to have a total of 3. So this is a helium atom with 1 neutron, 2 protons, 1 neutron. This isn't that stable. Helium-4 is definitely more stable, but this is an example of fusion. Whereas fission is the opposite. Fission is going to take a large atom and break it up into smaller pieces. So I'm just going to give a simple example of some smaller numbers. Let's go back to oxygen, and let's say we have a pretty unstable version of oxygen, which is going to be oxygen 18 again. And if we cause this atom to break down, which often is a result of adding neutrons So this would be the nuclear symbol for a neutron, 0 protons, but has an effective mass of 1. If we bombard this oxygen atom with a neutron, it could cause the atom to fissure. And so we'll see 2 daughter atoms, which aren't necessarily going to be the same. So I'm just going to show the possibility of 2 different atoms. Let's say out of this we get boron and lithium. So lithium is going to be 3 protons and boron is going to be 5 protons. And then I'm just giving you an example here. So I'm just splitting up the mass values, but I got to split 19 amongst this. So let's say that this is 9 and this is 10. So a really unstable version of lithium and a reasonably stable version of boron. Actually, I'll make this a little bit more realistic. Boron is more stable with 11. So just making sure that the numbers add up on the top and the bottom. Now, the part of this that I haven't been showing in the equation, but that's generally there, is gamma radiation. So during all these processes, what another product is usually energy given off. And one of the common ways that energy is given off for nuclear reactions is in the form of gamma radiation. So there is a particle that has 0 mass and is not a proton. This is a gamma particle, and gamma has this kind of a diving fish symbol, and it's 0 mass. It isn't a proton, so that's why it's 0, 0. It doesn't affect any of the mass values. It actually doesn't balance. You don't need it to balance these equations, but it's just a way of showing that energy is released. So these are the fundamental nuclear equations. Let's look at an example from a PDF that I'm going to post for you to try. So this is a worksheet that I've used in the past that I like, and very similar to the ones I've written. On the right side, it gives you a key of possible symbols. So these are the ones that could be used, or you may be asked to write a symbol of an element as well. So these could go in the box if they fit numerically, or another element that you may have to figure out. For example, number 1's already done, and this is one that I just did for you as well. But looking at number 2, we have a fill in the blank kind of question. What particle could go there if, let me zoom in a little bit so I can write a little bit better. What particle could fit in that box for number 2 if it undergoes an electron on the left side of the arrow? This is electron capture. Just to go back to one of the equation types that I showed you. So 18 equals something minus 1. So I have to go up a number. This should be 19. And there's going to be 0 change in mass. So this is going to be a 40. So whatever this thing is, it has 19 protons and a total mass of 40. So let's go down to the bottom and check. All the possible answers are on the bottom. And this one should be potassium. Element 19 is potassium. So my answer that goes in this box back up here. I think I almost got it. This is the element potassium. So I'd write a K in the box. And then for my answer, I'd write potassium 40, which is how we'd write the isotope potassium 40. So this is just a guess and check model, or a type of questions where you're guessing what goes in the blank. A little bit of this might be confusing. If you look at this right here, N is the symbol for a neutron, and it looks like it says 41, but this is actually 4 neutrons. If I can get my pen to work. This says 4 neutrons. So another way to write that would be 4 and then the symbol for neutrons. So when you're balancing the equation with the coefficient in there, I kind of imagine little parentheses around that, showing it's 4 neutrons, so that should have a collective mass of 4. So 106 and then a total mass of 4 on top, what's missing? Well, we started with 252, and so you have to do a little bit of math in your head. 106 and 4 gets you 110. So what else is remaining? So that should be 142. I'm not going to have numbers as big on the quiz. I'm going to keep it very simple, and it's going to be multiple choice. But this top number should be 142. That's the remaining mass, to make sure that all 3 of them on the right side of the arrow equals 252. And then what could go on the bottom if you have a 42 and 0, and you need those to add up to 98. So the missing piece to this is 98 minus 42, which is 56. And then you go to the periodic table and look up which one is 56. And then you can go down and check your answer. Or 142. So this would be barium 142. Element 56 is barium, and so my answer would be barium 142. I'm not going to ask you to do all of these. I'm actually going to, when I post this, I will have cut out some of the questions I don't think are relevant or maybe a little bit too challenging for how much time we've been spending on this. Also considering that we're not in the classroom, so I'm not going to be able to help you and assist you the way that we normally would be able to. So this is the last little bit on nuclear chemistry that I wanted you to look at, being able to look at nuclear equations and see where the neutrons show up in the equation, where the beta particles show up, and just simple balancing. And we'll be able to practice this again when we meet up later. I'm going to just have you try it out to start. You also have the crossword puzzle that's on the classroom post right now, and I have that set as a due date on Sunday, so you have a while to do that. But I'm also going to put this one online as well and have it due Sunday as well. So you have 2 assignments and a little less than a week to do those 2. And like I said, you'll see this assignment, but it's going to be clipped and cut. I'll probably just leave 10 of them for you to do. Let's take a moment to detour to our final review. So I want to go through the series of topics that I chose to include on the final quiz. This is going to be the quiz that I'm going to open up and give you a week to finish during finals week, second week of June. And there are several topics that we covered throughout the class that I'm not going to quiz you on. So if it's not on here, I'm not going to choose from it as far as my 20 questions that I'm picking. And you can see there's several different subtopics. So you might have more than one question about a subtopic. I may not ask about every single one of these, but this is the list that I came up with. So atomic theory kind of stems the very beginning of the class. What are the protons, neutrons, and electrons? Where are they? What is their charge? Relative mass? And what do they do for the atom? For an example, when we're talking about a proton and what it does, and if I were to just give all these qualities for the proton, a proton is in the nucleus, it's positively charged, it has a relative mass of 1. The neutron has a relative mass of 1. The electron has a relative mass of 0. And as far as its role for the atom, it's the identity of the atom. It's in the nucleus, it holds in the electrons, but the main thing it does is it's the identity of the atom. Our element name is based on how many protons. So that's the kind of analysis you're looking at when you're thinking, what is a proton, what is a neutron, what is an electron? And my thought was tomorrow I would go through these in more detail and essentially do a study session that I'll record and put online for you to use as a way of taking notes, reviewing, and you can bring all that material to the final. Atomic number, which we went over. If you have the atomic symbol, like for carbon, we looked at carbon 14. The atomic number is the 6. Atomic number is the 6. That's the number of protons. The mass number is that top left number. And you really only look at the mass number when you're talking about one atom at a time. Mass number is 14. That's protons and neutrons together. An average mass, that has to do when we have trillions and trillions of atoms and all their different isotopes are averaged. And that's something I'll go into more when we do our formal review. Isotopes, again, something I'll do much more of when we do our formal review. Nuclear chem deals with isotopes often. The short version is anytime you write an atomic symbol, you're talking about one atom at a time. You could also call it an isotope. Chemical bonding, I know we haven't done chemical bonding in a while, and I was a little stretched to include this, but I want you to know the fundamental difference between covalent and ionic bonding. This is definitely something I'll go over. And I want you to know how to identify the correct Lewis structure for water, ammonia, and carbon dioxide. I'll potentially ask about one of these, and I'll draw 4 different options, and I'll have you choose which one's the correct one. So metallic bonding is a little bit on metallic bonding, just to understand how the metallic bonding is arranged. Basically, it's all these metal atoms and all the valence electrons are free to move throughout the structure. And ionic bonding is definitely something I'll go into more when I do my review tomorrow. What is the octet rule? Noble gas electron configuration. So these were the main things that if you were to leave this class and go into another chem class at the college level and you're just starting out, these are some basic things that I think you should know to make you more successful going into a college level class. Again, I'm not asking about everything that we taught, and I'm just focusing on the fundamentals that I feel are the most important and the quickest to relearn, to be honest. Chemical equations, you got to know what a coefficient is, element symbol, reactants, products, arrows, subscripts. I may ask you to just finish one of the coefficients. I'm not going to have you balance an entire equation, but if I give you a couple of the coefficients, I might ask you to just finish the last one. And then if you're looking at a particular part of the balanced equation, you got to know how to read this. What is the 4? What does that 3 mean? What is C versus CL? Basic things like that. States of matter, just differences between solid, liquid, and gas. And again, this is something I'll go into much more detail of as far as what you need to know for the test, but I'm pretty much trying to write out as descriptively as possible what you need to know. Thermodynamics, we recently did thermodynamics, and I'm not going to do the calculation part of it. I'm mainly going to be assessing how do you know what heat flow is, or what is heat flow between 2 objects going from hot to cold, and the idea of when 2 objects touch, they're going to be transferring energy between each other. There's a little bit of thermodynamics in this kinetic energy part as far as between a solid, liquid, and gas, which has higher kinetic energy as a result of temperature. So again, no calculations, just a general understanding of how heat flows from one thing to another, or that heat flows from one object to another. So you're not going to see a whole lot of questions on thermodynamics, just some very fundamental concepts. And then nuclear chem is what we're doing right now. And there's a little bit of a longer list just because it's more current, and this should help drive our work in the next week as we finish nuclear chem and are reviewing for the final. But I'm only going to ask about an alpha particle or a beta particle with respect to their mass and charge, whether they're positively charged or negatively charged. And then a little bit of fundamentals about gamma radiation. So if you watched my previous lecture or watched the YouTube videos that I posted, it goes about these in great detail. And so those are ones to watch and review. Remember, this, you're taking this at home, so this is an open up quiz. So any little details you want to write down, go for it. And I'm also providing you essentially answers to the questions I could ask here, the way I've written some of them. We just went over fusion and fission in terms of the equations, but again, the videos give a great deal more information. the idea of what radioactivity means, what is radioactive decay, and when we saw in the equations, we saw the element changing, but just the fundamental reason, why does radioactive decay occur and what happens? So again, very fundamental ideas, but these are things that I'd like you to know going into a chem class in college. So this is my way of just assessing what you've learned. Relatively short list for a final, to be honest, but for 20 questions, I think I'll be able to write some good questions based off these. I'm going to use some questions from previous years, but I'm going to be writing them so it's a little bit more manageable based on the format that we're going to be testing. This, considering you're at home, it's open note, and it's just a final check. I'm not writing this quiz to tank your grade or raise it to grade levels. It's going to be a small adjustment to your grade, and on Friday, I'll have your essays done, and grades will be more current. So you'll see roughly where you're at and how this could affect your grade. So I'll be back tomorrow to record a study session, and then Friday you'll get an email talking about how grades are up to date, and you can go in and see how your score on a final could affect your grade. That's what I'm working on right now, and I hope everyone's doing well. I will talk to you soon, and hopefully you can show up tomorrow.